Hi everyone, my name is Daniel Vivas. I'm the product manager at SkyCiv Engineering. In this video, I'm going to show you how to use the SkyCiv API with a basic example. We'll create this parametric truss. We'll define some input data, such as the width of the truss, the height, and this spacing in the top chord. And basically we'll run multiple cases just using code in Python. So let's get started. Imagine that you have this structure and you'd like to know what would happen if I change this width from 10 to 15 meters, or what would happen if I change this height from 5 to 4.5, or if I change these spaces from 3 to 5, what would be the internal forces? To answer all of these questions, I could do some manual work. So I can modify all of these nodes coordinates. I could add more members here to check what would be the internal forces. But as you can see, it will take some time to create different cases for the same structure. In cases like this, when we have to do repetitive tasks to validate something, we can use this SkyCiv API because we can just create a small script with some input data, for example, the structure width, the structure height, and this spacing, and we can run this structure multiple times in a couple of minutes. Let's check now the SkyCiv page. We just have to go to the dashboard, click on this icon, and then on SkyCiv API. So this will open the SkyCiv page. The first thing that you can check here is this API authentication. You can click here and you will see your API username and the API key that you will use in your code. We can also see this API request and this API response. So basically we have here multiple examples that you can use to validate that your JSON structure is correct. So you can see this example for a structural analysis. If you want, for example, to create this pile design as per ACI 318, you can click here and you will see a full example of your data. So when you click here on Run API, you'll be able to see the response from the server. So you can test different cases using this API page. Here we have another example. We have this JSON data. We have some units, nodes, coordinates, and this will be the final result just by looking the 3D renderer. So let's check now the API documentation. In this documentation is everything you need to know to use this SkyCiv API. So you can check here the overview. We have a community. You can check here the use cases, the workflow. We have some videos that can help you. We have the explanation about how to use this request object. So you will see step by step these functions that we have. So as you can see, is pretty much the same that we have in this example, but you can see all the explanation in the documentation. It's also important to mention these API credits. So based on your subscription, you will have some credits for your account. So I'll show you later how to check that. You can see here this list of functions and associated costs for every function that we have. We have, well, the pricing, and check the pricing page, and you can track your usage of the API. We can also check this usage using the SkyCiv platform. So to check this API usage, we can go to the dashboard. We can go to account settings, API access. You'll see all the information that I showed you before about your username, the API key that you can use in your code. And this is the API usage. Now let's check the API documentation. So for example, we will be using this S3D model object, and we will be checking these properties that we can use in our example. So let's get started with the code. In this example, I'll be using Visual Studio Code. So the first thing that I'm going to do is create a new file called main.py. The second thing will be install the SkyCiv package. So I'm gonna do pip install SkyCiv. I already have it installed. And the last thing will be import the SkyCiv package so I can use all the functions inside of it. Now we are going to use the request object from the documentation. So we can copy this template, create a new variable called request data, and paste this dictionary. You can check the auth dictionary, so we have to get our credentials. So we can go to the account API, copy the username, paste it here, and then we can copy the API key and replace it. We have to change these Boolean values using a capital letter. That's the way how we do it in Python. And this last step, we are going to delete it because we are not going to solve our model in the code. So we can use this save data function that we have here. We have this name as Parametric Truss version 2. The path will be in the API folder and will be a private file. Now we have to create a model, so we can go back to the documentation, go to S3D model object, and select nodes. We can copy this object and paste it here. So now that we have a model, we can replace this model object. Before running this file, we have to create the request. So this request variable will be equal to SkyCiv.request. We can now import the JSON package so we can print the response in the console. We can run the file again. We're getting some errors here. So as we are testing our script, we are going to delete these options. And then we can run the file again. You can see here a response from the server. So it is telling us that everything went correctly. We have this data that is actually the link to the S3D file, and we have these functions that are every step that the SkyCiv API did for us. So let's copy the SkyCiv link. Let's paste it in the browser. And you can see that our nodes are created from the code. Now let's delete these nodes that we have here. We will import a package called math that we have to use to calculate the length of the top chord. Let's define the input parameters. First, we have the height of the truss, then we have the width, and finally, we have the spaces of the top chord. We can now create some calculations. We have to define the middle point, so this will be equal to the width of the truss divided by 2. We'll start defining the start point coordinates. This will be equal to a dictionary where we define the x, y, and z values. Then we can define the middle point chords. So the x value will be in the middle point, the y value will be equal to the height, and the z value will be equal to 0. Then we have the endpoint coordinates where the x value is the width and the other values are 0. We can now define the length top chord. To do this, we can use the math package that we imported before, and we are going to use the start point coordinates, the middle point coordinates, and the end point coordinates. Now we can define the step that we are going to use to calculate the coordinates. This will be equal to the length of chord divided by the spaces. And then we have the node index that must start with 4 because we already have 3 coordinates. This will correspond to a width, height, and the number of spaces, and this is the step that we are defining. Let's continue with the nodes creation. Here we are going to define a unit vector in the left top chords. For this we are going to use the middle point and the start point divided by the length of chord. The left top chords will be an empty dictionary. And now we're going to create a for loop. We're going to iterate over the number of spaces. We'll use the empty dictionary that we used before, where we have the space number, and we're going to define the x, y, and z coordinates using the start point coordinates, the unit vector, the step, and the space number. We have to increase the node index plus 1, and then we're going to do the same process with the unit vector in the right top chord. We're going to define an empty dictionary. Let's now create a for loop here with the number of spaces. In this empty dictionary, we will add these x, y, and z coordinates using the unit vectors, the step, and the space number. And we have to increase the node index one more time. Let's now create the bottom chord. We'll create an empty dictionary. Then we have to define the middle top chords. In this case, it'll be the internal coordinates. So we have the left top chord chords, the right top chord chords, and then we have the middle point chords. We're using this because we are going to extract the x value from these coordinates that we defined before. So we can create a for loop to extract the coordinates of this dictionary. Using the bottom chord chords, we are going to extract the x value, and the y and z value will be always be 0. We have to increase the node index plus 1. And finally, we can create this nodes dictionary, defining these 3 first points that we have here. And then using the spread operator of Python, we can use the left, right, and bottom chords. Defining this, we can save the model and run the script again. So if we reload our page, you can see that all of the coordinates are created. Let's proceed with the creation of the supports. In this case, we will use fixed supports and a roll support. So we can check here the restraint code that we're going to use. Now we're going to define the supports section in our code. We're going to create a new variable, and we're going to use these supports and these fixed codes that we have here in node number 1 and number 3. Then we are going to create sections for our model. So you can go to the documentation. You have many options to upload a section. We have one from the section builder. If you have your properties, you can use that dictionary. But in this case, we're going to use the ones in the section builder. So as you can check here, we have these American AISC W shapes, W413. So that's the one that we are gonna use in this example. So we can copy this part of the dictionary, and we just have to modify the name of that section. In this case, the material ID will be number 1, that corresponds to a structural steel. And now we can put the variables in the model. We can run the script. Let's load the page again. And you can see that our supports are created, and also you can check this section with the material that we defined before. Let's continue with the members creation. In this case, we have to change this line 82 to line 81. The reason is that we have these 20 node in the middle, but in order to create our members, it will be easier if we have a sequence of nodes. So if we change this node, now we have a sequence of our nodes in the bottom chord. Now we will have this members variable that will contain several members. So we have the ID, the node A, the node B. We have these fixities. Basically, we are going to use these fixities because we are using truss members and we don't want to transmit the moment to the other members. These are the members that will always be created no matter the number of spaces in the top chord, and these are the equations that you have to use to create them. If we run the script again, and we reload the page, you will see that these 7 members are created no matter the number of spaces that we have. Let's continue with the creation of the intermediate members. In this case, we will start with the member index equals to 8 because we already have 7 members created. Let's start with the left side. So we have this start node left side equals to 4. The end node left side will be equal to the number of spaces plus 2. That will correspond to this node. So now we have to create a for loop using the range of these two variables that we defined before. We have to use the same dictionary that we created before for the vertical members. So we're going to use this dictionary. We will add the node A, the node B will be equal to this equation. The fixities will be the same that we used before, and the section ID will correspond to the ID that we define in this section's dictionary. So we have to increase the member index in 1. So after we run this and reload the page, we can see that our vertical members are created. Let's continue with the diagonal members. In this case, we'll use the same dictionary. We just have to modify the node B equation. The fixities will be the same and the section ID will be the same. We can see here that our diagonal members are created. Let's now define the top chord members. We have to define a conditional here because we don't want to create the last member. So in the members dictionary, we just have to define the node B as the node plus 1. Because as you can see here, they are consecutive nodes. So let's proceed with the bottom chord. We'll use the same dictionary and these equations will change for the node A and node B, and we need to increase the member index in 1. So if we reload this, now we have the left side of the truss completed. So for the right side, I'm just pasting this code. We just have to change some equations that I'm highlighting. So it'll be pretty similar to the last step that we did with the left side. So if we run this again, you'll see that all of our structure is completed. So if we change the number of spaces, the height, or any input variable, you will see that it will still work because this is a parametric model. Let's continue with the point loads. In this case, we can check the documentation. We can click on point loads and we can see the different attributes that we can use, the different properties. In this case, we have this example and we have to take into account that we will apply these loads to a node. So I already have this dictionary that we can use. Basically, we'll have 3 loads. The first one will be applied to node number 2, the second one will be in the middle, and the last one will be in the last node. The load group for all of them will be a dead load, and we can define these point loads in our model and run the script. We can see here the loads that we just applied, and we can modify the input parameters. We'll use a width of 20 and a number of spaces equals to 11. As you can see, everything is working properly. Let's solve our structure. You can see the different results that we can obtain here. So let's check the reactions for our structure. We can also check the actual forces in the elements. And finally, let's check the displacement. You can see how it moves horizontally because we have the roller support in the node number 3. So let's now check how we can obtain these values also in the code. If we go back to the documentation to study_model.solve, we can check the different properties that we can use to solve our model. We can use the filter. In this case, we are going to copy this example. We will use a linear analysis type, and we are going to filter the member forces and the member displacements. When we run this, you can check all of the results in a JSON structure that are actually the same results that we are obtaining here. You have completed the parametric modeling tutorial using the SkyCiv API. I hope this tutorial has provided you with valuable insights into the process of modeling repetitive structures using the API of SkyCiv. If you have any questions or need assistance, our team at SkyCiv Engineering is always here to help. Thank you.